All right, so now let's think about how can we improve our model, right? So let's so what I'm noticing here, and you may have noticed this too, is that depending on our width, right? If our width is delta x, um, and let me start with, let's look at our n. So n is 4 here, right? So here we have this region from 0 to, yeah, I guess they don't give us the a and the b, but we have from a to b, right? And n is 4. So if we have 4 rectangles, that's going to give us a certain width, right? And we have a certain space in between them. So it seems like if we were to increase the number of rectangles, increase the value for n, then that would give us uh, smaller widths, and it seems like we would have smaller areas, right? Or smaller gaps, right? Smaller gaps there. And so that might seem to give us a more accurate depiction. So let's see what that would look like. So if we increased our n to 8 under the same curve, then we get smaller spaces, right? Smaller gaps. And let's say if we increased our n to 32, now we can see that we get super tiny gaps, right? So that's going to be an even more accurate depiction, right? Now there'll be more work involved, right? Because we'll have to find the area of 32 different rectangles and add them all together, right? So that's going to be more work, but it's more accurate. Okay. All right. And then same thing if we did right endpoint. That was left endpoint that we looked at before. If we did right endpoint, same thing is true, right? If our n is 4 in this case, then that means we're gonna have, this case we have excess, but we have bigger areas of excess, right? If we increase the size of n, which decreases the size of our delta x or width, then we have a little less excess, right? And then if we increase n to 32, now we can see that our excess is even more minimal, right? So the larger value we have for n, the more accurate our approximation of area under the curve will be, right? And here's an idea. So this is actually calculated for us in the book. So if n is 4, we have these approximate areas, right? For left endpoint and right endpoint is what those are. Okay, so we can see 7.5, 8.5, right? If n is 8, we get 7.75, 8.25, so we're getting closer. And then if n is 32, 7.94, 8.06, right? So it looks like the area is 8, or right around 8, and we can see that as we increase n, our value gets closer and closer. And this might remind you of limits, like as we approach a certain value, we're getting closer and closer to the given output. And so and if that was your instinct when you saw this, that's a good instinct, because limits will come back into play for a little bit. All right, so here this is called a Riemann sum, and it's basically just the sum of a bunch of rectangles, okay, on an interval from a to b. Okay, so we have some interval a to b, and delta x is the width of each subinterval, right? And remember, delta x equals b minus a over n. Okay, and then so this is our Riemann sum. So this is basically telling us our left endpoint, the length of our rectangle multiplied by the width of our rectangle, right? Remember, this is the height and this is the width. Okay, and we're going from 1 to n. All right, so that's a Riemann sum. And x sub I is some point in that interval. Okay, and the reason the asterisk is there is because we could either start at left endpoint x minus x, or x to the sub I minus 1, which would be x sub 0 really, or xi, which is starting at the right endpoint. So this is left endpoint and this is right endpoint. Okay. All right, and then and so now that Riemann sum, we talked about limits. If we say, hey, let's take that Riemann sum, let's take this sum of all the rectangles, and let's let's get as many rectangles as we can have so that this width is super tiny and we don't have any, that we minimize the gaps, right? And so that's where limit comes in, is we're saying, hey, instead of doing 32 rectangles, we saw what happens when we go from 4 to 8 to 32. Well, let's just keep going, right? Let's just keep going and go towards infinity. And so that's what this says, is, hey, let's just get as many rectangles as we can, and keep going, right, all the way to infinity. So as n approaches infinity, those spaces that we have, those gaps that we have, are going to get smaller and smaller and smaller, to the point where they're infinitesimal, to the point where they're insignificant. And so this is the formula for area under the curve, is the limit as n approaches infinity of the sum of all these different rectangles, of an infinite amount of rectangles underneath the curve, to the point where we have minimal error, right? Minimal excess and minimal minimal shortage, right? So where it's so insignificant that it actually equals the actual area. So this is actually a combination of limits and summation, right? And that's what the definite integral really is.